Hi, welcome all to the online classes. I'm Mukesh Bhardwaj, going to present a topic or going to deliver a topic Geiger Muller counter in engineering physics, BTech first year engineering. So Geiger Muller counter is basically is an instrument used for measuring the ionizing radiation, or basically we can say that it's a nuclear instrument. It detects ionizing radiation such as alpha particles, beta particles, and gamma rays using the ionization effect produced in Geiger Muller tube. It perhaps one of the world's best radiation detection instrument. So Geiger Muller counter is consists of a glass tube with thin central wire along its axis. The thin wire made from the tungsten act as an anode and copper cylindrical surrounded it act as a cathode. A high voltage between 800 to 2000 volt corresponding to Geiger region or plateau region is maintained between the wire and surrounding cylinder. The field in the vicinity of the thin central wire is always very high. The tube is filled with argon gas at a pressure about 2 to 10 centimeter of helium column. A small quantity of ethyl alcohol is introduced in the tube as quenching agent. The glass tube is provided with window of a very thin mica foil or cellophane or glass so that particles of a small penetrating power such as alpha particles or slow beta particles uh, can enter inside it. For the detection of fast beta particles, instead of taking a copper cylinder as cathode, it is often made by a thin layer of a colloidal carbon deposit on the inner wall of the glass envelope. In this way, beta particles can enter the tube from all directions. A resistance R is connected in the counter circuit, so the current pulse produces a voltage across it. The voltage pulse is then amplified and counted by electronic counter. So the basic principle of Geiger-Muller counter operates in a Geiger region. The ionizing particle passing through the tube ionizes the gases. An electron released by the ionization is accelerated towards the central wire. This electron acquires a very high velocity and produces large number of electron pairs by repeated collision with the atoms of the gas. Uh, The secondary electrons so liberated are also accelerated and more ion pairs are produced. This multiplication action is very rapid uh, and an avalanche result throughout the central wire. Thus, a large pulse of ionization current is produced and is independent of the number of primary electron ion pairs formed by the incident particles. Now, the quenching process is takes place after that. So, history, the original detection principle was discovered in 1908. The development of Geiger-Muller tube in 1928 that the Geiger-Muller counter became a practical instrument. It has been very popular due to its robust sensing element and relatively low cost. Operating principle Geiger-Muller counter or the Geiger GM counter consists of a GM tube, the sensing element which detects the radiation and processing electronics results in display. GM tube is filled with an inert gas such as helium, neon, or argon at low pressure to which a high voltage is applied and near about 2000 volt. Tube briefly conducts electrical charge when a particle or photon of incident radiation make the gas conductive by ionization. Operating principle, this is the GM tube pictorial representation. As you see this, the detector, the source, and the GM counter pulse counting electronics, and the supply voltage 1500 volt is nearly shown here. The ionization is considerably amplified with the tube by Townsend discharge effect to produce an easy measure detection pulse. Easy measure detection pulse. This large pulse from the tube makes the GM counter cheap to manufacture as the subsequent electronics is greatly simplified. Uh, the electronics also generates a high voltage, typically 400 to 600 volt. How it works: radiation dark blue is moving about randomly outside the detector tube. Oh, sorry. Detector tube. Some of the radiation enters the window, gray at the end of the tube. When radiation dark blue crash with the gas molecules in the tube, orange, it causes ionization. Some of the gas molecules are turned into positive ions, red, and electrons, yellow. The positive ions are attracted to the outside of the tube, light blue. The electrons are attracted to a metal wire, red. Running down the inside of the tube, maintained at high positive voltage. Many electrons travel down the wire, making a burst of current in circuit connected to it. The electrons make a meter needle deflect. If a loudspeaker is connected, you can hear a loud click every time particles are detected. Application for the detection of alpha and beta particles. To detect radioactive rock and minerals in the course of mineral prospecting or as a mineral collector. To check for environmental levels of radioactivity. For fire and police first responders to analysis of making an initial determination of radiation risk. The main characteristics of GM counter and its limitations: the height of the pulse voltage is constant and does not depend on the primary ionization. Pulse voltage is produced even if a one electron ion pair uh, is generated in the chamber. For the entrance of ionization particle, the paralysis time is quite large, so it limits its uses. The height of the pulse voltage does not depend on the energy of the ionizing particle. Therefore, GM counter cannot be very used for measuring the energy of particles. However, it is very useful for counting beta particles entering into the GM counter. Alpha, beta, and gamma cosmic particles can be detected by the GM counter. The GM tubes have a limited life due to decomposition of organic vapor used as quenching agent. And it has a large paralysis time of about 200 to 250 microseconds, which prevents its use at very high counting rate of above 5,000 particles per second. And it cannot provide information regarding the nature of ionizing particle, whether it is charged particle or photon, or it cannot detect neutron as it does have ionizing property and hence cannot activate the GM counter. With the field, this stage corresponds to the top of the magnetization curve. The model discussed above accounts successfully for all observed aspects of magnetization such as hysteresis, remnant flux density, and coercive fields in polycrystalline sample. Crystalline boundaries act as an obstacle, having a variety of barrier heights to the wall movement. There is no single threshold field for the one set of irreversible motion of a domain rotation, and the magnetization will have the sharp and loop as shown in the figure. In ferromagnetic materials, it is possible to exert some control over coercive force SC by taking advantage of the fact that domain wall motion occurs more easily than magnetization rotation. In permanent magnetic material, it is desirable to have large values of SC through separation of domain boundary motion. A high coercivity is assured. This is generally accomplished by using materials consisting of two metallurgical phases, which give a heterogeneous structure. Two ways for aligning a material magnetic domains: growth of favorably oriented domain initially, then the rotation of domains finally. Means material used for transformer core should have low hysteresis losses and high permeability. In this case, low value of SC is desirable and is achieved by making a material pure, homogeneous, and well-oriented to facilitate domain wall motion. This gives higher permeability as well as lower value of SC. Sufficient experimental evidence exists to support the domain theory. A simple technique involves the proportion or preparation of colloidal suspension of ferromagnetic powder. When a drop of this suspension is placed on the carefully prepared surface of ferromagnetic crystal being studied, the colloidal particles gather along the domain boundaries. This phenomenon is due to the fact that adjacent domains are magnetized in different directions, resulting in strong molecular fields at the interfaces. This technique is due to bitter and pattern is called bitter powder pattern. Nowadays, more refined techniques are available which allow domains to be observed in motion. One relies on the Kerr magnetic optic effect. Here, polarization light is reflected from the magnetized surface to adjoining domains being magnetized in the opposition direction or opposite direction produce a positively directed rotation of the plane of polarization. When the reflected light is viewed through a microscopic, it can be arranged that one domain will appear light and the neighboring dark. Now, next, magnetic domains applying very strong fields can saturate magnetization by creating single domain. The hysteresis curve. Hysteresis curve means lagging or retarding of an effect behind the cause of the effect. Here, effect is magnetic field density and magnetic field intensity, also called BH curve. Hysteresis curve is known as BH curve. Hysteresis is magnetic materials mean lagging of magnetic induction or magnetization behind the magnetizing field H. Before starting to the hysteresis or hysteresis curve, I would like to give some detailed explanation of magneto restriction, which we had earlier discussed, that when a ferromagnetic material is magnetized, changes in physical dimension in general occur. This phenomena is known as magnetization magnetization, not magnetization. This phenomenon known as magneto restriction. Three types of magneto restriction is generally referred to. First one is longitudinal magneto restriction, which is change in the length in the direction of magnetization. This change may be increase or decrease in length. Transverse magneto restriction, change in dimension perpendicular to magnetization direction. And the last third is volume magneto restriction, change in volume resulting from the above two effects. In converse of magneto restriction effect, the Villari effect is also observed. in magnetic materials where a longitudinal deformation leads to change in a permeability in the direction of applied strain. In general, material which extends on magnetization will have its permeability raised by tensile strength or tensile strain, whereas for a negative lambda material, an external applied pull reduces the permeability. Magnetorestriction has largely of theoretical interest and of limited practical applications. There have been some application to high frequency oscillators and to generators of super sound. Magnetorestriction is also used for underwater sound projectors and sound detectors. The magnetic permeability is related to magnetorestriction, and for high permeability materials, application and effort to is made to keep magnetorestriction as low as possible. So this is all about the magnetorestriction. Now we are discussing the hysteresis curve. As we had already know about the hysteresis curve in earlier classes, while studying the transformer, if you memorize or memorize, when you study the transformer, at that and there we had studied the hysteresis curve. A hysteresis curve is just like a leaf-like structure which gives a graph between B and H. Between B and H, so hysteresis curve means lagging or retarding of an effect behind the cause of the effect. Lagging and retarding of an effect behind the cause of effect. That is, the cause which produces the effect, so that effect is lagging, somewhere lags and somewhere lead or somewhere retard due to the cause of effect. Here the effect is magnetic field intensity and magnetic field effect and magnetic field density and magnetic field intensity, also called BH curve. Hysteresis in magnetic material means lagging of magnetic induction or magnetization behind the magnetizing field or intensity. Next, this is the hysteresis curve. By observing the figure, you come to know some terminologies. That is, first, the curve is between B and H. On horizontal x-axis, we take H, and on y-axis, we take flux density, that is B. There's some points which are shown in the red color are the points of some terms. When you are at the position of A, the position of A indicates the saturation level. When you reach to the point B, it is the point of retentivity. When you reach to the point C, it is the point of coercivity. When you reach to the point D, saturation in opposite direction. And again, it will, a closed loop curve which is depending upon the magnetic flux of line. Next, ferromagnetism, magnetic hysteresis. Now, we are going to discuss the ferromagnetism and its magnetic hysteresis curve. So, first, in ferromagnetic substance, the magnetic moment of adjacent atoms are also aligned in opposite, but the moments are not equal, so that there is net magnetic moment. That is, if the net magnetization of magnetic substance is not zero, the material exhibits a net magnetic moment. However, it is less than in ferromagnetic materials. This moment disappears above a Curie temperature Tc, analogous to Néel temperature, at which thermal energy randomizes the individual magnetic moments and the material becomes paramagnetic. Ferromagnetic materials, which have wide application in electrical engineering, have a disadvantage that they have low electrical resistivity. The lamination used for electrical machines have resistivity of about 14 into 10 to the power minus 6 ohm centimeter, and the highest value obtainable in ferromagnetic alloys is less than 10 to the power minus 4 ohm centimeter. This disadvantage of the ferromagnetic materials limit their application in the high frequency alternating current applications. High eddy current losses and poor magnetic utilization of metals occur in sheets even at the low frequency. Ferrites, on the other hand, with useful magnetic properties, have DC resistivity of many orders of 10 higher than in iron and are used for frequency up to microwave in transformer core. So the magnetic hysteresis hysteresis curve for ferromagnetism. This is the saturation magnetization. Next, M1 is saturation remnant magnetization. Coercive force, the field needed to bring the magnetization back to zero, that is retention or retentivity. So, reverse saturation and then the same procedure again to the saturation magnetization. So, for example, the barium ferrites are the most important type of ceramic permanent magnetic materials. They have much higher values of coercive force than alnico alloys. They have high resistance to demagnetization, about 3 times more, and high electrical resistivity, about 10 to the power 6 times than alnico alloys. These ferrites are composed of Ba, barium oxide, iron oxide, anisotropy produced during manufacturing make these as permanent magnetic material. Ferrites are magnetized by applying large external fields. Barium ferrites are used as focusing magnets for television tubes and in small DC motors in compact torque drives. The other types of ferrites used as permanent magnet. Ferrites are soft magnetic applications are mixed ferrites having in their composition metals like this. So some ferrites possess the hysteresis loop shown in the slide, which have been used earlier as a. Still, other ferrites are used as components of electric electronic ferrites, microwave device, magnetic computers. For memory and switching devices, these materials are used in the form of thin films. Next, hysteresis remains and coercivity of ferromagnetic material. So, this is the detailed discussion of a hysteresis loop. Hysteresis. If you observe the figure and the contents written in the boxes, just go through the figure and the contents written in the boxes. Now, material magnetized to saturation by alignment of domains. What do you mean by this saturation region? When materials are magnetized and they align themselves in a domain, alignment of domains, then the saturation level reached. When driving magnetic field drops to zero, if I'm just talking about this point, when driving magnetic field drops to zero, the ferromagnetic material retain a considerable degree of magnetization. This is useful as magnetic memory device. And if I'm talking about on this particular point, the drawing magnetic field must be reversed and increased to a large value to drive the magnetization again to zero. So towards situation in the opposite direction. So when you just again or you it comes to zero when you are reverse the field, the domains will align in the opposite direction and the reverse saturation point is reached at this point. Okay. Now the hysteresis loop shows the history dependent nature of magnetization of ferromagnetic material. Once the material has been driven to saturation, the magnetizing field can then be dropped to zero and the material will retain most of its magnetization. It remember its history. Now, if I'm talking about this point, that is remains a measure of remaining magnetization when the driving field is dropped to zero. This is saturation. This is coercivity, a measure of reverse field needed to drive the magnetization to zero after being saturated. This is the reverse saturation, the strength of magnetizing field, and the this is all is given. So remnant magnetization is equal to m naught and coercivity is equal to SC. Now, these are the hysteresis curve or loops for hard and soft magnetic materials. So, before discussing these graphs, I'll let you know what you mean by the soft magnetic material and the hard magnetic materials. Application wise magnetic material, mostly ferromagnetic material, which are used in almost all electric devices, can be classified as soft and hard magnetic material, depending on the ease with which the direction of magnetization can be altered by an applied magnetic field. That is, the division is based on the value of SC shown in the hysteresis loop. The same of the hysteresis loop of the magnetic material is of great engineering importance. Soft magnetic materials are easy to magnetize and easy to demagnetize. This enables them to reverse magnetization rapidly in response to alternating electric field, where they are required to concentrate magnetic flux in transformers and inductance. With a standing alternating current of frequency 50 Hz, the core traverses the whole hysteresis loop 50 times a second. To minimize the energy lost during the cycle, the area with the hysteresis loop should be small as possible. Materials having small hysteresis losses are soft magnetic materials. Soft magnetic materials form the magnetic circuit in an electric machine. An ideal material for this purpose is one exhibiting the highest possible permeability and saturation flux density and the lowest possible cone loss. Normally, machines' performance specification dictate the material to be used for given application. For small rating machines, it is normally the cost. Now, hard magnetic materials are hard to magnetize and hard to demagnetize. High value of residual flux density and coercive force characterize these materials and make them excellent permanent magnets. The former establish the higher induction field needed to strongly attract ferromagnetic materials. The latter prevents magnetic effect from being influenced or even destroyed by the nearby magnets on external fields. This combined requirement is usually assessed by BH maximum, which should be large. Material with large BH maximums are called hard magnetic materials. So, when we are comparing the hysteresis loop for soft and hard materials, if the iron specimen is carried to saturation at both the ends of magnetization, then thin loop is called as the saturation or major hysteresis loop. And three quantities are defined as Bs, highest value of flux density called saturation flux density when the iron specimen is carried to saturation at both the ends of magnetization curve. The residual flux density Br on the saturation loop is called retentivity. The coercive force Hc on the biggest BH is called coercivity. The retentivity of the substance is the maximum value which the residual flux density can attain, and the coercivity, the maximum value which the coercive force can attain. For a given magnetic material specimen, no points can be reached on BH diagram outside the saturation hysteresis loop, but any point inside can. So, this is for the hard ferromagnetic material having large MH and large Sc. The area of the hysteresis loop is related to the amount of energy dissipation upon the reversible of the field. Now, the hysteresis loop for soft ferromagnetic material has both a small M0 and C. A narrow hysteresis loop implies a small amount of dissipated energy in repeated reversing the magnetization. So, soft magnetic materials form the magnetic circuit in electrical machine like transformers, motors, etc. They should have low hysteresis and eddy currents losses. The materials for the cores must be easy to magnetize and demagnetize. In 50 Hz supply, the core traverses the whole hysteresis loop 50 times a second. Iron losses, eddy current and eddy current losses. So iron losses or core losses is the energy which is dissipated in the form of heat within the core of electromagnetic device when the core is subjected to alternating electric field. The core losses are traditionally separated into two components, hysteresis losses and eddy current losses. So the hysteresis loss is due to the form of intermolecular friction, and the eddy current, the term eddy current refers to the circulating electrical current which are introduced in the sheet of conducting material when it is subject to alternating magnetic field. These eddy currents produce more power which is dissipated as heat. The eddy current loss at frequency which are low enough for inductive effects to be neglected in the given by general equation. The different types of material used as soft magnetic material fall in three groups: alloy based on iron, nickel iron alloys, and ferrites. So this is the soft and hard ferromagnetic material, and there is hysteresis loop or hysteresis curve. For hard material magnetic material, we see that the curve is wider, and for soft it is narrower. Magnetic field strength versus flux density or magnetization. So if you observe the graph at the starting, that is the origin, when there is no magnetic field strength is applied or the flux density is zero, then the magnetic field strength is zero. As you just go on increasing the magnetic field strength, the alignment of the or the spin of the electron is random at zero, so the output is nullified and the magnetic effect cannot be observed. But slowly or gradually, when you increase the flux density or magnetization, the electron spins align themselves in a uniform direction, and at the highest point all the spin are in same direction, resulting the high magnetization, and it is known as the saturated magnetization. Again, the hysteresis curve showing the same phenomena of varying magnetic field. Now, this is the tabular difference between the hard magnetic materials and soft magnetic material. Hard magnetic material have large hysteresis losses. Soft magnetic have low hysteresis losses. Domain wall moment is difficult. Domain wall moment is relatively easier. Coercivity and retentivity are large. Coercivity and retentivity are small. Um, wait a minute. Coercivity and retentivity are large. Coercivity and retentivity are small in soft magnetic material. Cannot be easily magnetized and demagnetized. So the hard magnetic material are not easy to magnetize, or once they get magnetized, they are not easy to demagnetize. Whereas soft magnetic material can be easily magnetized and demagnetized. Magnetostatic energy is large, magnetostatic energy is small. Have small values of permeability and susceptibility, have large values of susceptibility and permeability, used to make permanent magnets, used to make electromagnets. Iron, nickel, aluminum alloys, copper, nickel, iron alloys, copper, nickel, cobalt alloys, iron, silicon alloys, ferrous, nickel, nickel alloys, ferrites, and garnets are the example of soft magnetic material. Now the quiz time or the question: basic source of magnetism. Charge particle alone, movement of charge particle, magnetic dipoles, magnetic domains. Units for magnetic flux density: Weber per meter square, Weber per ampere meter, ampere per meter, Tesla per meter. Magnetic permeability has units. Option A, Weber per meter square, Weber per ampere meter, Option C, ampere per meter. Option D, Tesla per meter. Magnetic permeability has unit as Tesla. Option B, Henry. Option C, Tesla per meter. Option D, Henry per meter. So just give the answers or choose the options according to your knowledge. Or magnetic field strength units are. These are the simple fundamental questions or the quiz which are based on the example for diamagnetic materials, superconductor materials, superconductor, alkali material, transition metals, and ferrites. So, what are the examples of diamagnetic materials? Choose the option. Question number 7. Example for paramagnetic materials, superconductors, alkali metal, transition metal, ferrites. Question number 8. Example for ferromagnetic materials, superconductors, alkali metal, transition metal, ferrites. Examples of or for antiferromagnetic materials. Option A, salts of transition elements. Option B, rare earth element. Option C, transition elements, metals. Option D, ferrites. Question 10, example for ferromagnetic materials. Option A, salts of transition elements. B, rare earth elements. C, transition metals. D, ferrites. Question 11, magnetic susceptibility paramagnetic material is plus 10 to 5, minus 10 to 5, 105, or between 10 to 5 to 10 to 20, 10 to 2. Magnetic susceptibility of diamagnetic material is, among all the four options, you choose the appropriate answer. So these are the hints and the answers. Thank you. Thank you all for today's lecture. Now we are going to start with new topic in the next lecture, which is the introduction about the insulators, conductors, and semiconductors, and in continuation to that, we are moving to the superconductors. So thank you all. Thank you.